Let's talk about a breakthrough that's making robots move with a lot more grace. We're diving into why so many advanced robots have this strange, hesitant pause, and the surprisingly simple software fix that's finally making them fluid, fast, and, well, a little more like us.
You've definitely seen this in videos, right? A robotic arm goes to pick something up, and right before it does, it just stops. For a split second. It's this tiny, awkward stutter. It just feels unnatural. Well, it turns out the reason for that little pause is really fascinating.
And here's the thing. It's almost never a problem with the robot's physical parts. The motors, the joints, they're all perfectly capable of moving smoothly. The real issue isn't in the robot's body, it's in its brain. It's all about how the robot is processing information and deciding what to do next.
Okay, so if it's a brain problem, not a body problem, let's get into it. We're going to call this the robotic pause problem, and we're going to figure out exactly why these incredible machines need to take a little break. The technical term for these pauses is idle frames, and it's exactly what it sounds like. The robot is literally idle. Think about it like this. You're trying to cook a new recipe that you have to stop everything you're doing, put the knife down, turn off the stove, just to read the very next line of instructions. That's what the robot is doing. It makes a move, then stops dead in its tracks while it waits for its brain to compute the next command. Only then does it move again.
To really understand why those idle frames are even a thing, we've got to look at the traditional way robots have been taught to think. It's a process called synchronous inference.
And first, let's just quickly define that word inference. You can basically think of it as the robot's thought process. It uses its cameras and sensors to observe the world around it, and then its AI model crunches that data to decide on the best next action. It's the robot's version of us thinking, okay, there's the door, I need to reach out my hand and turn the knob.
And this slide just lays out that old synchronous process perfectly. The robot observes, it thinks, and then, this is the absolute key, it waits. It physically cannot move while it's thinking. Imagine a chef who chops one single carrot, then stops everything to read the next step, then picks up one onion, stops again to read the next step. It works, sure, but it's incredibly slow and inefficient. That wait step right there, that's our idle frame. That's the pause.
But now there's a much, much smarter way to handle this. It's called asynchronous inference, and honestly, it is a total game changer.
Now, look at how simple and powerful this difference is. The old way, think, then act. The new way, think while acting. The secret is basically decoupling the thinking from the doing. The robot is always moving, executing a list of commands it already has, while its brain is simultaneously figuring out the next list of commands.
And hey, don't just take my word for it. The source material puts it perfectly. The next action chunk is computed before the current one is exhausted, resulting in no idleness. It's like the robot is given a to-do list, and before it even gets close to finishing, the next to-do list is already there, ready to go. The waiting just vanishes.
Let's go back to our chef. This is the pro chef now. They're not stopping to read a recipe between every single step. Oh no. While the onions are in the pan cooking, they're already chopping the garlic for the next step. They are thinking and acting at the same time, in parallel. That is the kind of fluidity and efficiency asynchronous inference brings to the table. So how on earth does this actually work? Well, the magic is in this really clever setup that's almost like giving the robot two brains that work together, one that's in charge of doing and one that's in charge of thinking. So first up, you have what's called the robot client. Think of this as the robot's body, its local nervous system. It lives right on the machine itself. Its job is super simple. Use its cameras to see the world, stream what it sees to the main brain, and then just execute the action commands it gets back. See and do. That's it. And then you have the policy server. This is the big, powerful brain. And it doesn't even have to be on the robot. It can be a huge computer running in the cloud. It gets the video stream from the robot, runs these massive, complex AI models to figure out, say, the next 50 moves, and then it sends that chunk of actions back to the robot. And while the robot is busy carrying out those 50 moves, the brain is already working on the next 50. Now, this system is incredibly elegant, but it's not just a plug-and-play solution. To get that perfectly smooth, fluid motion for a specific task, engineers have to fine-tune a couple of really important settings. To get it just right, engineers basically have two main dials to play with. First, as you can see here, is actions per chunk. That's literally how many moves the big brain sends in each package. A bigger chunk is safer, less risk of the robot running out of moves. But if the chunk is too big, the plan might get stale if something suddenly changes. The other dial is the chunk size threshold. This tells the robot when to ask for a new list. Should it ask when it's halfway through its current list, or wait until it only has a few moves left? Getting this balance just right is the secret sauce.
It really is a balancing act. You're making a trade-off. Do you need the robot to be super responsive, constantly getting fresh plans? Or is it better for it to execute a longer, more precise set of motions without being interrupted? By tuning these dials, you can optimize the robot for anything, from performing delicate surgery to rapidly sorting packages in a warehouse.
So, when you put this all together, what does it really mean? Why is getting rid of a tiny little pause such a big deal? Well, it fundamentally changes what robots are capable of. So let's just recap the big takeaways here. First, obviously, it kills that frustrating lag. That means we get much smoother, more reactive, more natural robot behavior. And here's a huge one. Because all the heavy thinking is done on a separate, powerful server, the robot itself doesn't need a supercomputer strapped to its back. And that means we can use much, much larger and more powerful AI models to guide them. And all of this together makes robots way more adaptive and capable of dealing with the messy, unpredictable, real world. And that really leaves us with a pretty mind-blowing final thought. For years, the robot's physical body has essentially been waiting around for its digital brain to catch up. With asynchronous inference, that bottleneck is finally being removed. So, if a robot's body and its brain can finally work in perfect, fluid sync, what will they be capable of next?